Hello, we are Team Efish, and this is our Shalico Marathon Phase 2 presentation. About us, we are engineering and robotics students from Saratoga High in the Silicon Valley. We got interested in clean energy and are now on a mission to make the innovations that save the world. FTC, the first tech challenge, our first project as a team, which introduced us to robotics and engineering. Our next project was the Silicon Valley Bike to the Future event. In this, we won third place and we had a very effective dual hub motor design. This really sparked our interest in energy efficient battery electric vehicles. Our next competition was FRC, First Robotics Challenge, in which over 3.7K teams participated and were tasked to design and build bots to compete in a challenge. We were the fifth seed alliance in the world and we had an innovative claw and lift system. The next step in our journey was Shalico Marathon. This is the electrical part of our battery electric vehicle. This is our energy supply diagram. Our electrical system consists of a three-phase BLDC outrunner motor that is throttled with the use of a twist throttle and the Arduino Uno. These parts are powered with the use of a DC-DC power converter and a large lithium polymer battery. The Arduino will act as a microcontroller managing the horn, brake, and the throttle inputs. We have bought a twist throttle from Kimis as our steering system is of a bike. As for the motor, the Turnigy Aerodrive, it is a three-phase brushless motor that is manufactured for model airplanes. It has a maximum voltage of 44 volts, max current of 70 amperes, and runs at 149 kV. Powerful enough to move the vehicle at 15 miles per hour. Our battery system consists of our 12S 44.4 volt lithium polymer battery. This then goes through a series of kill switches required by the Shell Eco Marathon. These switches are the two kill switches required, one for the driver and one for the at the rear of the car. It eventually reaches the DC-DC power supply, which will give power to the Arduino and the DRV8312 motor driver. So, our motor controller. It consists of the DRV8312 motor driver and the Arduino Uno acting as a microcontroller. The Arduino Uno will handle interfaces such as serial, PWM, USB, and analog. It'll take in the throttle input, um, sends signal to the driver to determine voltage, and the DRV8312 basically acts as an interface between the motor and the microcontroller, in this case being the Arduino Uno. It will man power for the motor and takes low current signal and converts to high current signal.
Let's move on to the hardware side of things. So we began our hardware design with a structural frame for the car. The material we're using is 6061 welded aluminum tubing. We iterated through dozens of frame designs until we landed upon one that performed at a sufficient safety factor while not sacrificing weight. With components we added in later, like the aluminum flooring for the driver, our safety factor rose further. Our simulations tested loads from the driver and electronic components. We also tested external loads being applied in all directions on the roll bar and safety harness mounting points. We'll be using a fiberglass shell around our car. Over the course of the design process for this shell, we use SolidWorks fluid simulations to do CFD analysis and optimize the shell, minimizing drag. There are a few driver safety features that need to be mentioned. To begin with, we have allowed about 480 millimeters of space in front of the driver's feet as crumple zone in case of a head-on collision. Additionally, we have measured out the roll bar such that the minimum distance from the driver's head to the roll bar is about 90 millimeters. An aluminum bulkhead separates the driver entirely from the propulsion compartment. Finally, we have created a large driver hatch and a propulsion compartment hatch on the shell for easy access. This is the propulsion compartment in our car. Going from the motor, we designed a custom gearbox as per our calculations for the required speed and torque to get up inclines and average 15 miles per hour. We are using gear on gear to transfer power from the motor to the wheel to maximize efficiency. Our custom gearbox will use Teflon coated steel gears. We have checked to ensure that the gearbox can manage the torque from the motor. These are some visuals of our front and rear steering and braking. Um, our steering is on the front wheels. We are using an Ackerman steering system. We have checked in our steering geometry that we will be able to complete the 8-meter turning radius. We are using 15 millimeter steel spindles that can bear a cantilevered load. For braking, we are using a hydraulic braking system. We have one 60 millimeter rotors in the front and a 180 millimeter rotor in the rear, which will provide sufficient torque needed to stop us on an incline. We're using a single master cylinders that go to 2 calipers for the front wheels. Let's quickly list out the major specifications of the car. The maximum height is about 700 millimeters. Our wheelbase is about 2,500 millimeters. Our track width, which is also our maximum width, is about 1,100 millimeters. Our vehicle length comes out to 3,400 millimeters, and the weight is just at about 50 pounds. These are just some 360-degree views of the car. Let's talk about manufacturing. So we'll be entering a 2-week manufacturing phase after the end of our school semester next week. We have planned this out so that we will definitely be able to finish in the 2 weeks. We have acquired all of our required parts. This is mainly the aluminum tubing and sheeting for the frame build. Additionally, we've built all 3 wheels. We have all of our steering parts, the tie rods, rod ends, spindles. We have the gears for the gearbox. We have the braking parts. And we have all required fasteners and bearings, including some 3D printed parts for the gearbox. So we're also partnered with BART Manufacturing, which is a leading Silicon Valley metal manufacturing company. We have access to their shop and equipment for our build, and this ensures that we'll have the equipment and expertise to finish our build in the December build period and be fully prepared with a car on the track by April. Additionally, we have sponsorships, local support from Automation Anywhere, and we're also finalizing a sponsorship with Silicon Valley Clean Energy, our local energy company. Thank you for your time.